Hi, I'm Nisar Patel. I'm going to talk about how to verify multi-copy search structures today. This is joint work with Siddharth Krishna, Dennis Shasha, and Thomas Wies. Okay, so let me start off by explaining what these multi-copy search structures are. These are data structures which implement a key value store, and these data structures are optimized for write-heavy workload. So the insertions and updates must be handled very efficiently. The simplest way to handle these updates is to just add the updates at the root node. Deletions are also handled in the same manner as the update by using a tombstone value. Together we call this operation the upsert operation. Search, on the other hand, starts at the root node and returns the first copy that it can find. Now, as more and more data is added to the data structure, the root node becomes full, and so the maintenance operation slowly flushes the data downstream. Now, if in case of conflicts, the old data is overwritten by the new data. So what is the goal for this work? Well, in practice we see many multi-copy structures, the main example being the LSM tree or the log structure merge tree. These data structures, these implementations differ from each other not only in how the nodes themselves are implemented as in the inner structure, but also the outer structure, which could be a list, a tree, or a DAG, an arbitrary DAG. So verifying these implementations individually is a difficult and it's a challenging task. So the way we want to approach this problem is we want as much proof reuse as possible. We want the proof of one implementation to be useful towards proving other implementation as well. Now, what do we mean by correctness? Well, what we want to prove is that these implementations satisfy map-ADT, which is to say that these implementations basically represent a map from keys to values. The upsert operation basically updates the map, while the search operation returns the value of the key under this map. Now, this specification is expressed in terms of atomic triples. In order to prove this triple, we have to find a single atomic step in this operation such that before this step the precondition is true, and after which the postcondition is true. Now, for the upsert operation, it is easy to find this point. This point is also called the linearization point, by the way. This point for upsert is exactly when this new k, v pair is added to the data structure. However, for the search operation, it is not very clear when this point will be. In fact, the linearization point of search is affected by the concurrent upserts. To see that, consider the following example. We have a multi-copy structure with two nodes, right? And in this example, we have attached timestamps with the values. This is to distinguish between two different values which are attached with the same key. Timestamps are not part of the data structure, but merely just ghost data, useful for the purpose of the proof. Okay, so in this scenario, let's say that we have a thread which is looking for key k1. It starts at the root node, does not find it, and goes to node n. Now it goes to sleep, and concurrently there is an upsert operation which adds k1, 8 to the root node. Now the search thread wakes up and finds k1, 4. Now this is not the point where it can linearize, because search found k1, 4, but it is not the most recent copy in the recent copy of k1 in the data structure, as that one is k1, 8. So the post condition is not true at this point. In fact, the point at which the search could be linearized was at the beginning, even before its execution started, because at this point k1, 4 is the latest copy. Now, but again, always linearizing at the beginning also does not work, because you can imagine that it is possible that the search in a different execution, search actually reads this k1, 8 if instead of traversing to n, if it was still at node at the root node. But generally, the insight here is that if v0, t0 was the most recent copy of k when search begins, then the search operation returns one of these two values. Either it returns the same v0, t0, in which case it has not been affected by any of the concurrent upserts, or it returns a pair v, t such that t is greater than t0, which means this pair has been added to the data structure after v0, t0. So in this case, it returns something that was added by a concurrent upsert. This property is called search recency because essentially it says that search returns something which is at least as recent as what it started with. In the first case, the strategy is to linearize at the beginning, as we saw with the example. In the second case is where actually the proof is complicated and the search operation needs to be linearized by the upsert operation. This phenomenon is called helping. Now, without going into that proof at this moment, the reason why the multi-copy structures are linearizable is because of search recency. So let's look into why search recency holds true for multi-copy structures. So the main reason why it holds true is because of this invariant which is maintained by the multi-copy structures. The invariant says that the first copy for any key, the first copy that is reachable from the root node is also the most recent copy of that key. For instance, for key k1, the first copy that is reachable from the root node is k1, 6, and it is also the most recent copy, as the other copy has timestamp 3, which is less than 6. So essentially this invariant is maintained because of how the upsert and the maintenance operation are designed. Upsert just adds the new copies at the root node, while the maintenance operation overrides the old copy and preserves a new one, which maintains the invariant. This invariant makes sure that the search starting from the root node finds the most recent copy or a newer copy by an upsert. So essentially why this holds is because of the high level algorithm for upsert, search and maintenance. Now if you look at the implementations in practice, and if we ignore the aspect about the inner structure and the outer structure, about how the nodes are implemented and whether it's a DAG or a tree, those implementations also follow the same high level algorithms. So to take advantage of that, we introduce what you call a template algorithm. A template algorithm is an algorithm which abstracts away from the details about the inner and the outer structure and provides us a way to describe the algorithm at the high level. So let me show you an example of the template algorithm for the search operation. Search operation calls the recursive procedure traverse. Traverse checks the contents of node n using a helper function called inContents. Now the definition of inContents depends on how a node is implemented. So this template algorithm is applicable to data structures, implementations which use any possible search structure to implement this inContents function. If it does not find a key, then it moves on to the next node with the help of, again, a helper function called findNext. Again, findNext, depending on if this node is part of a DAG or a list, provides a way for the search to go to the next node. So essentially, this template algorithm covers all sort of varieties of this LSM trees. Okay, so what is our plan now? Our plan is then, so we want to show that all these implementations satisfy search recency first, because search recency leads to linearizability of these data structures. And instead of directly showing search recency, we first introduce template algorithms, and we actually show that it is the template algorithms which satisfy search recency. So okay, to show that the implementation satisfies search recency, we break down the proof into two parts. Template algorithms, first part is the template algorithm satisfies search recency, and the second part is that this assumption, the template algorithms make an assumption about how the helper functions will behave, and the second part will show that the implementations actually satisfy those assumptions. Right. Okay. But okay, so this makes things easier. This simplifies the problem because search recency can be expressed using specifications which has fixed linearization points. So the proof that a template satisfies search recency is easier than directly proving the map ADTs. Now we are not quite done yet, because our final aim is to show that these implementations satisfy map ADT specification. However, so our approach then is to prove the map ADT specification assuming search recency. This proof has to deal with the non-fixed linearization point of search, basically implement the strategy for linearization points that we talked about earlier. That strategy is implemented using a helping protocol. Helping protocol needs to take care of things like at what point shall a search thread engage in helping, or it matches up right upsert and search pairs for helping, things like that. So that's what is part of this proof. The beautiful thing about this is that this proof is common across all templates. It does not rely on anything in any aspect of the template. So it is common across all templates and has been factored out. So this proof is done once and for all and is applicable for all templates of the multi-copy structure. So let me summarize this story so far. So what we have is that what we started with is that we have implementations of multi-copy structures, and we want to prove that they satisfy map ADT specification. Proving it directly is hard because of non-fixed linearization point and the complex invariance even. So what we do is introduce search recency and simplify the problem first. Now we see that the high-level algorithms which guarantee search recency are the same across all implementations. So we introduce template algorithms to simplify and increase the proof reuse further. Finally, we show that search recency implies map ADT specification, and again this part is independent of independent of the templates. So this part is true and holds for all templates. So essentially we get proof reuse at 2 points. By introducing templates, we achieve proof reuse across implementations, and by factoring out search recency, we achieve proof reuse across the templates. Using this methodology, we have verified 2 templates: LSM DAG template, which is for variants of LSM trees with DAG as an outer structure, arbitrary DAG, and a differential file template, which are precursors to LSM trees. As part of this template, we have also verified the maintenance operation, which transfers data from to the downstream nodes. LSM implementation that we have verified uses an unsorted array as the root node and a sorted string table as the data structure for the disk for all the other nodes. Finally, we use the higher order concurrent separation logic iris and SMT based automated program verification tool called Grasshopper for different parts of the proof. So let me just leave you here with this slide. Thank you.